Today we have section 4.4. We're going to look at graphing functions that have asymptotes. The functions that have asymptotes are typically rational functions, things that have a numerator and a denominator, where there are powers of x in the numerator and denominator. Some functions will have only vertical asymptotes. Some will have no vertical asymptotes, only horizontal asymptotes, whatever. We're just going to have to figure out how to do this. We've already talked about vertical asymptotes. A vertical asymptote occurs where there's not a value of the function. So we say the line x is equal to a is a vertical asymptote if the denominator of this fraction is 0, but the numerator is not. If they're both 0 at the same place, when you take the limit, you can cancel that common factor and it shows up as a hole in the graph. So I've given you 3 examples to show you what kind of asymptotes they have. Let's look at each of those. The first function has a constant in the numerator and x plus 2 in the denominator. So you can see when x is equal to negative 2, then f is not defined. And what happens there? We've got a shift of the graph of 4 over x, 2 units to the left. Remember, the graph of 4 over x does something like that and that. The graph just rips apart at x is negative 2, okay? Because the denominator is 0. So this is the vertical asymptote for x is negative 2. Now look at g. G of x has 2 vertical asymptotes. Sorry, not a 2. That's supposed to be a 1. X minus 1, x plus 1. So it has 2 vertical asymptotes at x is equal to 1 and x is equal to negative 1. So the graph rips apart twice. To get the other features of the graph, you'd probably need to do maybe take derivatives or something like that to find whether the graph is increasing or decreasing. H of x has a factor of x plus 1 in the numerator, so when we factor h of x the way we did g of x, we see that the factor of x plus 1 is a common factor. That means there's a hole in the graph at x is negative 1, and the vertical asymptote occurs when x is 1. So that's how you find vertical asymptotes. Near vertical asymptotes, the graph becomes infinitely large or infinitely small, as this graph did here around the x minus 2. Horizontal asymptotes describe the long-term behavior, what the tail ends of the graph are doing. If the graph is essentially, if the value of the function is essentially constant when x is a really big number, either a really big positive number or a really big negative number, then it kind of tails out like a horizontal line. To find the horizontal asymptotes, then, we need to look at computing limits to infinity. The first example is kind of obvious. We're letting x get really large, and so if we do this, this thing kind of acts like 4 divided by a really large number plus 2. Well, adding the 2 to a really large number doesn't put much of a dent in it, but I've got 4 divided by infinity. So the bottom is really big. Divide that into 4. I can make that as close to 0 as I want. So this limit goes to 0. That means the function f of x is equal to 4 over x plus 2 has a horizontal asymptote of y is equal to 0. Now go back up and look at the graph that I drew. I did draw the tail ends of the graph right here, getting close to the x-axis, because I knew that that's what was going to happen, and that's what this says down here. I'm going to use this idea to help me to evaluate the limit that I've written next. The idea was that if I have a constant divided by a really big number, then I'm essentially going to get 0. In fact, if I have 1 over the variable to a power, this numerator doesn't have to be 1. It could be a 4. It could be 10 million. Just any constant divided by x to a power. When x gets big, that constant gets chopped up into a bunch of little pieces so small that it'll go to 0 as x goes to infinity. So let's call that a fact, and that's the fact that I'm going to use when I compute all of these limits. So here we are looking at the limit as x goes to infinity here, and I've got a bunch of x's on top and x's on bottom. And I'm going to try to do some algebra to it so that I can rewrite this where there are terms that look like constants divided by x to a power. The quickest way to do that is to divide each term in this expression by the highest power of x. So here I see x squared is the highest power of x. Let's rewrite this where I divide each term by x squared. So I'm going to have a 3x squared over x squared plus 4x over x squared plus 5 over x squared. And then downstairs we have 7x squared over x squared plus 2x over x squared plus 3 over x squared. And one little simplifying step here, let's reduce the x's where we can. I can get a 3 plus 4 over x plus 5 over x squared, and 7 plus 2 over x plus 3 over x squared. Now these are equivalent fractions, even though they look very different, and I'm allowed to do this divide by the highest power of x stuff as long as I'm away from 0. Well, we are away from 0. We're going to infinity. Now I look at the terms that have an x in the denominator, and I use my fact from above that those terms will vanish as x continues to grow. So everything disappears, and all that we're left here is the 3 and the 7. And that's my limit. And then I would say the line y is equal to 3 over 7 is the horizontal asymptote for that original fraction. Now let's try one more here, and then I've got to point something out to you. We're going to do this dividing by the highest power of x. In this expression, the highest power of x is also x squared. So let's rewrite this fraction as x squared over x squared plus 4 over x squared. Then that's divided by 6x over x squared plus 2 over x squared. So I'm looking to take the limit as x goes to infinity. I'm going to get a 1 plus 4 over x squared and a 6 over x plus 2 over x squared. And now let's mark the terms that are going to vanish when x gets large. Anything that's a constant over an x is going to go to 0. And so in this example, we're going to be left with 1 plus 0 on top and 0 on the bottom. Well, that's going to be infinitely large. This limit does not exist. It's getting real big. So this type of function will have no horizontal asymptote. The tail ends of the graph either both turn up or both turn down. Those details, again, we can get by graphing this using the first derivative in increasing and decreasing. So in general, the line y is equal to L is the horizontal asymptote for a rational function if, when you take the limit as x goes to infinity, you get the number L. Now, if you continue to do this by dividing by the highest power of x, maybe you'll see that if the highest power of x is in the denominator, then the denominator will grow faster than the numerator, and the horizontal asymptote should be y is equal to 0. If the highest power of x is the same, it's no coincidence that the horizontal asymptote, or the value of that limit, is the ratio of the coefficients of that highest power of x. And then if the degree on top is bigger than the degree on the top grows faster than the bottom, which means in the long run, the y values get infinitely large. So we can use that pattern to our advantage and save us a few steps. If the degree on top, the degree of the numerator, is equal to the degree of the denominator, if top and bottom have the same degree, the limit will be the ratio of the coefficients of the highest power of x. Always. If the degree on the bottom is bigger, in other words, it's bottom heavy in power, like our first example, the bottom is going to continue to grow while the numerator essentially kind of stays steady, and so we'll eventually get 0 as our limit. If the degree on the bottom, the denominator, is bigger than the degree on the top, the limit will be 0. Bottom heavy. If the degree on the top, or the numerator, is bigger than the degree of the denominator, then there will be no limit. The limit is infinite. Plus infinity or minus infinity, we don't care. We can figure that out with the derivative or something like that. But so if the powers are the same, just look at the ratio of the coefficients. If the bigger power is on the bottom, limit is 0. If the bigger power is on the top, the limit will be infinite. And whatever the limit is the horizontal asymptote. A horizontal asymptote is a line, so you're going to write the equation of the line. Y is equal to that number. It's the horizontal line. So what we're going to be interested in doing is identifying asymptotes and graphing these functions that have asymptotes. So let's look at an example. Let's look at f of x is equal to x squared divided by 4 minus x squared. So the first thing we should notice is that there are two places that make the denominator 0. 4 minus x squared is equal to 0 when x squared is 4, and that's when x is 2 and x is negative 2. Those are our vertical asymptotes. Now I'm going to identify the horizontal asymptote. For the horizontal asymptote, notice that the degree on top is equal to the degree on the bottom. So both numerator and denominator grow at the same speed. That means the horizontal asymptote is the ratio of the coefficients. I got a 1 in front of the x squared on top, a negative 1 in front of the x squared on the bottom. So I would say y is equal to negative 1 is the horizontal asymptote. Or if asked another way, I'm saying that the limit as x goes to infinity of x squared divided by 4 minus x squared is equal to negative 1. The ratio of the coefficients. Okay. So what we know so far is that there are 2 breaks in the graph. So here's what we have so far. At negative 2 and +2 we have asymptotes that way, and at -1 we have a horizontal asymptote that way. So what we've got to figure out is what's happening to the graph in each of these areas. Well, the graph is either going to be up here and stay up here, or it's going to be down here and stay down there. Same thing in the middle. The graph is either going to be up here and stay up here, or be down here and stay down there. Then we've got this region over here, up and below. So we got 6 pieces of the graph that's of interest to us. What I'm going to do is I'm going to find where this function's increasing or decreasing by using analysis of the first derivative. Oops, got the wrong point on here. Let's get that off, get back here. Get that off, and let's go back to a nice sharp point. Okay, let's find intervals where this is increasing and decreasing, and that'll pretty much give away what the graph looks like. So we need the derivative, and that'll be found using the quotient rule. We've got the bottom times the derivative of the top minus the top times the derivative of the bottom all over the bottom squared. Let's multiply it out. I'll have 8x minus 2x cubed plus 2x cubed all over 4 minus x squared squared. So the 2x cubes are gone. My derivative looks like this. So notice that the derivative is going to be 0 only where the top is 0. And that's at x is 0. We still have 2 discontinuities in this thing at 2 and -2. So when we analyze the sign of the derivative, let's make sure we put those 2 discontinuities in here. 0 and 2. So remember, we're going to remind ourselves that that's an asymptote, and that's a critical number. And now let's get the sign of f prime. I'm looking right here. The denominator is squared, so when I'm away from 2 and -2, the denominator is positive. So when I plug numbers in here, plug in a -3, I get a negative. Plug in a -1, I get a negative. Plug in a +1, I get a positive. Plug in a 3, I get a positive. So the direction of the graph is that it decreases and decreases, then it increases and keeps increasing. That means this critical number has to be a min. So I have that it decreases to the left of that first asymptote, then it continues to decrease between the asymptote and the min, then it's going to increase between 0 and 2, and then from 2 on out. So let's go back and put it together for the graph. Let's draw our asymptotes at the 2's. Go back up here and put 0 in for x. F of 0 looks like 0 to me. And now I'm going to draw in here in a different color. I've got to decrease, but I have to have my vertical asymptote. I guess I better put my horizontal asymptote, in here. The horizontal asymptote was at -1. So, if the graph is decreasing and the left end of the graph has to hug this line, then which of these two is possible? Does the graph do this or this? Well, it clearly can't do that because this end doesn't go toward the vertical asymptote. So let's take that away. It can't do this. Now let's look in the middle. I've got a min here, so the graph has to drop, turn around, drop, hit my min, and go back up and not cross the vertical asymptote. The middle has to look kind of like a parabola. Now the rest of the graph to the right-hand side of 2 has to increase. So the question is, does it increase like this or like this? Keep in mind, the right end has to head toward the horizontal asymptote. So this is out of the question. It has to follow the line this way. So now let's draw it in with our blue pen. It's got to hug that asymptote and hug that asymptote. It's got to hit the minimum in here and then hug the asymptotes out there. If you wanted to punish yourself, you can look for the change in concavity, but that would involve doing a whole lot of algebra to that little fraction there. So we'll kind of fake our way through it just by looking at the first derivative. Here's where I'd say, are there any questions? But I guess you'll have to ask me your questions online. Usually, if a function has a horizontal asymptote, it'll have only one. But there are some cases where it has different asymptotes on the left and on the right. And that's usually going to happen when we've got a square root somewhere. So let me give you an example of a function by taking the limit, say, as x goes to infinity of x plus 2 divided by, say, the square root of x squared plus 9. Then we'll do the same thing as x goes to minus infinity. Now, I said we'd look at the degree on top and on the bottom, but my claim is they're the same degree. The square root of x squared behaves like x. Kind of. Remember that when I take a square root of something, it has to be positive. So this operation happens first, and then I take the square root of it. So if I had something like a negative 4 squared, the square root of negative 4 squared is not negative 4. It's positive 4. Because I do the squaring first. I can't take the square root of a negative number. So technically, the square root of x squared behaves like the absolute value of x. So when I do this limit here, I have a positive number acting like another positive number because it's the absolute value of x. And so this limit should give me 1. Let me do the dividing thing. Let's divide the numerator and denominator by the highest power of x, which is x to the first power. But now if I want to divide this by x to the first power and move it inside, I'd have to write that x to the first power as the square root of x squared. And so this thing simplifies. Let's get rid of this junk over here. Get out of my way. This thing simplifies as 1 plus 2 over x, and this simplifies as 1 plus 9 over x squared. And so as x goes to infinity, these little fellers disappear, and we're left with 1. So we do it again, except this time when we do all of these same steps, this fraction right here is going to act like not a positive 1, that's going to act like a negative 1 because we're getting big negative numbers. This is going to act like taking the limit as x goes to minus infinity of x over the absolute value of x. And so in this case, this thing goes to minus infinity. Right? The numerator will be negative, but the denominator is going to be positive. So this would be an example of a function whose right end goes to positive 1, but whose left end goes down to minus infinity. Something like this. I don't know what happens in between, but the right end heads toward positive 1, and the left end heads toward minus infinity. Maybe something like, maybe. That's just a guess. Okay, so you'll need to practice finding horizontal and vertical asymptotes. We can describe the behavior near asymptotes with limits, and then you need to be able to sketch the graph of asymptotes. Also, there's a bit in here about cusps. Cusps of a function occur where the graph has a sharp corner. We can find those because that'll be a critical number. So it'll be a critical number where the derivative does not exist, where there's a zero denominator of the derivative, but not in the original function. We'll also have places in the graph where the tangent line is going to be vertical. So here f prime does not exist. That kind of thing happens maybe like f of x is x to the 1/3. This kind of thing happens maybe with f of x is x to the 2/3. This one, since it's a cube root, is defined for all values of x, but its derivative is going to have a denominator, so that's going to give us a sharp corner. Same deal here. I've got cube root, so it's defined for all x. Its derivative is going to have a 0 in the denominator. What makes this one, what makes them have their shapes is the concavity. So it's the second derivative that's going to tell us, oops, that's a concave up, silly. We look at the second derivative to decide what happens where the derivative fails to exist. So I'll go over some more examples on Blackboard Ultra of how to find these asymptotes and what they mean graphically. Look over my notes. I've got some worked examples in those. But for now, that's what I want to say about section 4.4.